A car is traveling at a constant velocity of 10 meters per second. So it's traveling at a constant velocity of 10 meters per second. When the driver sees a child 50 meters in front of him, his reaction time to hit the brakes is 0.5 seconds. He then hits the brakes to stop the car. The car accelerates at negative 1.5 meters per second squared. Will the car hit the child? So remember what we said, the first thing we do is we always draw a little picture. Even if we're a terrible artist, we draw a picture. So here is our car, which is a little box. It is traveling at a constant velocity. So our VI is 10 meters per second. 10 meters per second. There is a child and he sees the child, which is 50 meters away from him. 50 meters. But his reaction time is 0.5 seconds. So it takes 0.5 seconds before he hits the brakes. The car then accelerates at a negative 1.5 meters per second squared. And they want to know, will he hit the car? So the first thing we need to do, step one, we need to know how far he traveled, during his thinking time. And during his thinking time, or his reaction time, and during his reaction thinking time, he's not changing his velocity. So we know the velocity is change in displacement over change in time. Remember I said to you the only time you can use this equation when we're going at a constant velocity, which we're doing now. So therefore delta x is equal to v delta t. So therefore we've got that his velocity is 10, and the time is 0.5, which means he's already traveled 5 meters during his reaction time. Now, and I'm changing color so you can see which part of the question I'm doing. Now we need to know when he starts braking, we want to know how much distance does he have. He's already used up 0.5 meters. 5 meters. We need to see how much he's going to use. So, initial velocity is still 10 because he only starts braking now. His final velocity, because we want him to come to a standstill, is 0. He wants to stop the car. He hits the brakes to stop the car. The acceleration is negative 1.5, okay? And we want to know his displacement. We want to know, does he stop in the right time or the right displacement? So again, let's look at our equations. I'm going to write them down here. We've got VF equals VI plus A delta T, but we don't have the time, so we're going to cross that out. But we've got VF squared equals VI squared plus 2A delta X, and that one works perfectly, so we're going to use that. So VF squared equals VI squared plus 2A delta X. The final velocity is 0. The initial velocity is 10, but it's squared, plus 2 times by minus 1.5 delta x. So therefore, this we take across, it's 100, we take across, becomes a minus 100 is equal to minus 3 delta x. So the delta x is going to be minus 100 divided by minus 3. So our delta x equals 33.33 meters. So he takes another 33.33 meters. So in total, he has traveled 5 meters during his thinking time plus the 33.33 meters, which equals 38.33 meters. So lucky for us, yes, Will the car hit the child? No, the child survives. Why? Because he had 50 meters and he only traveled 38.33 meters. But grade 10s, please make sure you understand this. Understand that you need to think about your thinking time. And when your parents are driving, or your friends, your older friends, or whatever, and they're driving faster than they should and they're not leaving a good 2-second gap, explain to them nicely that you don't want to die today. Okay, please be careful.